Griffiths E&M section 5.4.3, the multipole expansion of the vector potential. Now, we've written so far expressions for the vector potential that involve the current of a wire and adding all of those little bits of wire up. Okay. So you have some arbitrary wire shape, current is going in a particular direction, and you have some little bit of that wire, and then you use that to find the magnetic vector potential at some point in space. Okay. So this picture I've drawn so far is independent of your choice of coordinates, but you can choose an arbitrary origin, and then you are able to define r prime and r from that. Okay. So just like we did for arbitrary charge distributions, we can also make an approximation here for the value of 1 over script r. 1 over script r, we did this before, becomes 1 over r times the sum of all of the Legendre polynomials, r prime over r to the n, bn cosine of alpha, where alpha is the angle between r and r prime. We did this before. Okay, so I guess so far this is not an approximation. This is exact. You have all infinite Legendre polynomials. But we can go ahead and write out the first couple terms in a nice grouping. This vector potential at some point in space is equal to mu naught I over 4 pi, 1 over r, the closed path integral of dl prime, plus 1 over r squared, closed path integral r prime cos alpha dl prime, plus some other higher order terms. Unlike in the case of the electrostatic multipole expansion, this integral here is always 0. Right? I add up all of the paths along a closed loop. That gives me 0. Right? So if I imagine I have the vector sum of all of these discrete steps, which is the discrete analogy to this integral, the average of all those vectors is 0. Okay, so that goes away. That is the monopole term. This is one of the reasons why they say that there is no magnetic monopole. All right, so if that's the monopole term, then this is the dipole term. And therefore, we can ask specifically about the dipole term. What does that look like? Well, mu naught I over 4 pi, 1 over r squared, integral of r prime cos alpha dl prime. And just like we did previously, we're going to use this expression to build a moment. Now, it's not going to be an electric dipole moment, but it's going to be a magnetic dipole moment. So I'm skipping 2 lines in the textbook on page 253, but that allows me to then rewrite this as mu naught over 4 pi, 1 over r squared, our magnetic dipole moment crossed with r hat. This is the magnetic dipole moment, which is defined as the current integrated over a surface, or I times A. Okay. So I have a path, let's say I have a square loop, and current is going in this direction, I. my magnetic dipole moment is related to the current magnitude times the area, which is now a vector. So I know how to calculate the area of this from geometry, and now the direction of that is going to be pointed up because we are using the right-hand rule with the current here. So if I'm going in a loop with my current, I curl my hand in the direction of those currents, and my thumb points up. So now my area vector points up.